Lesson 5.4, Inequalities in one triangle. In this lesson, we'll take a look at how sides and angles relate to each other. Theorems 5.9 and 5.10 talk about the connection between a side length and the angle directly across from it. It says the longest side is opposite the largest angle. Taking a look at XY on the far left, we have a side length of 11. That means angle Z at the bottom would be the largest angle. If 11 is the longest side, then Z is the largest angle. Now on the right-hand side would be the opposite of that. The shortest side in the triangle is opposite the smallest angle. If 5 has the shortest length for ZY, then angle X is the smallest angle. Down below, we've got a compound inequality that compares them. Taking a look at the first row, these are side lengths. And they're written from shortest to longest. So when I say what is the longest side, we wouldn't give an angle answer. Down below, we've got angles. And angles are smallest, well, that's an A right there, smallest to largest. Notice X is less than Y, which would be less than Z for the angle measures. Now the triangle inequality theorem underneath talks about the sum of any two sides in a triangle and how it must connect to the length of that third side. It says the sum of the lengths of any two sides must be greater than the length of that third side. So take a look. We've got the 5, the 8, and the 11 on triangle XYZ. Notice we're taking any two sides and adding them together. So this entire left-hand side would be the sum of any two sides, no matter which two you pick. Now the right-hand side, this is always the third side. And the inequality in between them means greater than. We're going to do some work with these inequalities throughout this lesson. We're starting off our examples with a fill in the blank. If B is greater than A, that means side length B is greater than side length A, then we also could recognize that angle B would have to be greater than the measure of angle A. If one side is greater than the other side, then the corresponding angle would be greater as well. Our next example, list the three sides of PQR in order from shortest to longest. Well, what we need are all the angle measures first. So we need our angles first. We have two of them, which is great. Angle P is 48 degrees and angle Q is 83 degrees. In order for us to get angle R, we have to take 180 minus 83 and minus 48. Go ahead and enter that into your calculator and see what you get. 180 minus 83 minus 48 should equal 49 degrees. That would be the measure of angle R. So now we know the three sides of PQR in order from shortest to longest. The shortest side is always across the smallest angle. The smallest angle is P, therefore the shortest side is segment QR. That segment is less than the next one, which would be across 49, and that's PQ. And that side length is less than, take a look at angle Q, 83 degrees all the way across, segment PR would be the longest side. Let's see if we can apply that to our next example. Example 3. What side of triangle KLM is the longest? So now we don't need all of them in order, I just want to know the longest side. Well, again, like up above, we need to know all the angle measures in order to determine this. So to get the measure of missing angle K, if we take 180 minus 50 and then minus 62, you should get 68 degrees. So angle K is 68 degrees. Now to determine the longest side, remember the rule is it's always across the largest angle. Out of the three angles in this triangle, K is the biggest angle. Therefore, side length LM is the longest side. Our next example is another fill in the blank, and this has to do with the triangle inequality theorem. Given the triangle with the sides A, B, and C, A plus B, the sum of those two side lengths, has to be greater than side C. But if I change it up and add B and C together, their sum has to be greater than side length A. And then the last option, if I add the two sides A and C, those two side lengths have to be greater than the other side length B. Now hopefully this will help us with the examples down below. Example 5. Which set could be the sides of a triangle? Set 1 has side lengths 18, 19, and 40. I'm going to let side 19 be lowercase a. And side 18 is lowercase b. And side 40 will be lowercase c. And what I'm going to do is take these three situations and test them down below. First, if A plus B is greater than C, then we know that that inequality is true. But if we take 19 plus 18 and say that that's greater than 40, well, 19 plus 18 is only 37. Is 37 greater than 40? No, for sure it's not. What would end up happening on these three side lengths, if we drew the 40-inch side length at the bottom, and then try to put the 19 over here on one side, and the 18 on the other, the 18 wouldn't connect. There's a missing amount that would be able to connect them, because 18 plus 19 isn't greater than 40. For set 2, the side lengths are 33, 37, and 66 meters. So again, let's test that little a, little b, and little c inequality set up above. Now if we take a plus b and set it greater than c, that would be 33 plus 37 is greater than 66. Well, if we add 33 and 37, we get 70. And 70 is in fact greater than 66. So a plus b, which has to be greater than c, would be true in set 2. But we have to test all of them. That's the thing with the triangle inequality theorem. Let's try b plus c. Is that greater than a? B is 37, c is 66. So yeah, that's definitely going to be greater than 33. 37 plus 66 is 103. And that checks. So we have one more. Let's take a plus c and test if that's greater than b. A is 33, C is 66. I think we're going to be great here. 33 plus 66 is 99. That's greater than 37. True statement. Therefore, set 2 is where the triangle is possible. Our next example in triangle DEF. If D is 6 and E is 11, what are the possible values of F? So if D is 6, that means it's going to be directly across capital D. I'm just going to put a little 6 down here. And lowercase e is 11. That's directly across big E over here on the right. What are the possible values for F? Well, we know that using our triangle inequality theorem, if we add F and 6 together, they have to be greater than 11. To get F by itself, if I move 6 over, I know F has to be greater than 5 in order for that triangle to work. Let's see, what else do we know? F plus 11 has to be greater than 6, but watch what happens here. we get f is greater than -5. Well, we can't have a negative side length, and if it's greater than -5, +5 right here would take care of that. So this one doesn't really help us in our final answer. But our last scenario, we do have to double check. Side lengths D and E, so 11 plus 6, have to be greater than the other side. This means 17 is greater than F, or, that's an R right there, F, wow, try that. F has to be less than 17. So we have two scenarios here, everybody. We've got F is greater than 5 and F is less than 17. So here's how you use both of these as our inequality solution. What are the possible values for F? If F has to be greater than 5 and less than 17, we put 5 on the left, and then F in the middle, and then 17 on the right. As long as the side length for F is between 5 and 17, that triangle will be possible. Okay, on to our final example on triangle ABC. It says AB is 25. So AB is over here on the bottom right. That's the same as lowercase c, 25. BC is 42. So let's take a look at BC. That has to be 42. Oh, hang on, get that 2 in there. True or false? AC equals 9. That would have to be this segment right here. Is it possible for AC to equal 9? Well, let's see. If we take 42 plus 9, is that greater than 25? Yeah, that would be 51. So that's true. What about 25 plus 9? Is that greater than 42? Well, 25 plus 9 is 34. 34 isn't greater than 42. So this triangle isn't possible. Therefore, can AC equal 9? Does AC equal 9? That statement is in fact false. And this is using side lengths and angles in one triangle. Lesson 5.4.